In this section, we're going to study quadratic functions. Specifically, we'll look at two forms we can write their equations in, standard form and vertex form, and then in class, we'll take a look at solving applications involving these functions. All right, so first of all, what is a quadratic function? A quadratic function is one in which you're going to have an x squared term, an x term, and a constant term. Now, the x term could be 0 or the constant term could be 0, but the key is that there is definitely an x squared term involved. So the way you see it written here, ax squared plus bx plus c, this is what's known as standard form. Another way that we tend to write it is in vertex form. And so you can also write them like this. And the significance of vertex form is that the vertex, which is either the bottom of the valley or the top of the hill, is always going to be hk. So the advantage to having it in vertex form is you can read where that minimum or maximum value is just right off from the equation itself. Notice there's a minus sign here, so if h is positive and it says x minus, like let's say x minus 2, so if I had y is equal to 4 times x minus 2 squared plus 4, then I would say that the vertex is 2, 4. But if I said y is equal to, say, 3 times x plus 1 squared minus 3, then I would say that the vertex is -1, -3. So whatever sign is in front of the k, that's going to determine the y value of the vertex, but then it's going to be the opposite of what you see next to the x to determine the x value of the vertex. And then finally, whether a parabola, which is the name we give a quadratic function's graph, whether that parabola opens up or opens down is determined by whether the a out in front here or the same a that's up here is positive or negative. So positive means it opens up, and negative it means it opens down. All right, so first of all, what we have here is a function in vertex form. So suppose they want it written in standard form. Okay, and remember, standard form means we're saying we want f of x to look like ax squared plus bx plus c. All right, so all I have to do here is start off with my vertex form and realize that x minus 5 squared really just means x minus 5 times itself. So I'm going to have to FOIL all that out in order to write it in standard form. So I've got the 2 out here, and we're going to keep it out there, but now I'm going to go ahead and FOIL everything. So I've got x squared minus 5x, so first, outside, inside, and last. And I can further combine those two like terms in the middle, so x squared minus 10x plus 25. And then, of course, my 2 should distribute to each term. So this will be 2x squared minus 20x plus 50. And then we've got that minus 14, and of course I put the 50 and the minus 14 together. So 2x squared minus 20x plus 36 is this function now written in standard form instead of the vertex form. And both standard form and vertex form have their purposes, and we'll see what those are as we go through various examples. In this example, we're going to basically go the other direction. So we're going to give a function that's already in standard form, write it in vertex form, and then we're also going to find the horizontal and vertical intercepts to help us graph this function. So first of all, let's remember what we're shooting for here. With vertex form, we are looking for a function that looks like this: a times x minus h squared plus k. So this function that we've got right here needs to look like this. So in other words, it's got to have this quantity of x minus or plus a number squared. And so what we need to do is create a perfect square within this expression here, but we've got to do it in an algebraically legal way. So what I'm going to do is I'm going to start by writing out the function that we have, x squared minus 6x, and then I'm going to leave a bunch of space here. I'm going to put plus 7 way over here. Now what I'm doing is I'm leaving all this space because what I want to do is I want to add something in order to make it so that this factors in to a perfect square, so something that would look like the x minus h squared portion. But I know if I'm just going to add a number, I have to make up for that by subtracting that same number. Okay, so we're going to try to figure out what goes in this blank spot. So to do that, what I want to do is think about what I want to have happen. I want this to break down into two identical factors where we have x and x. And so when it breaks down, and so what I'm specifically looking at here, let me kind of color code this a little bit, is I'm looking at this portion right here to turn into this portion right here. Okay, so we're just going to focus on that piece of it for a moment. So the question that we ask at first is, okay, how do I ensure that this multiplies out to make this? Well, first let's look at this middle term. This middle term needs to be negative 6x. And where does that come from? It comes from the outside plus the inside. So we ask ourselves the question, what numbers do I put here and here so that the outside plus the inside is negative 6, and so that these two are identical? Well, the answer, of course, is negative 3, right? If you put a minus 3 here and here, then the outside is negative 3x, the inside is negative 3x, which would add to make negative 6x. Well, by understanding that, we also have answered the question of what gets put in this empty space. So in that empty space, I know that I need to put the last, right? That when you FOIL out, this constant term will be the last times the last. So that's going to be negative 3 times negative 3 is positive 9. Okay, now if I'm going to put positive 9 there, I have to put minus 9 here, so that at the end of the day, I'm really just adding 0. So this red piece here turns into all this, and then my minus 9 plus 7 turns into minus 2. So that would be this part right here turns into, oh, my minus sign went away. There we go, minus 2. And with that, I can say, well, then that's equal to x minus 3 squared minus 2. And there is my function in vertex form. Okay, so that's great. So now I know where to put my vertex, right? I can see that my vertex, remember the vertex is positive 3, so it's the opposite of the sign you see in here with the x, and it's exactly the same as the sign for the k that you see. So 3, negative 2, so I can go over 3, down 2, and this is going to be the vertex of my function. I know it's going to open up because a is positive 1. All right, but the other thing it asked me to do is find the horizontal and vertical intercepts. Okay, so first of all, my vertical intercept, or in other words, my y-intercept, is where x is equal to 0, right? So really all I have to do is say, well, what is f of 0? And honestly, I think I'm going to go back to the original way I wrote the function here because that's really easy to see. You can see the answer is just going to be 7. So that constant that's all by itself. So the vertical intercept is 0, 7. All right, so we'll count our way up here to 0, 7. Okay. And then let's also talk about our horizontal intercepts. So horizontal intercepts are when y is equal to 0. Okay, so in this case, I'm going to use the vertex form of our function here. So the y, or the f of x, is equal to 0 when x is what? So add 2 to both sides. So this will be 2 is equal to x minus 3 squared. All right. Now when I have a number squared is equal to 2, I can get rid of the square by taking the square root. Okay, so x minus 3 equals the square root of 2. The only thing I got to be cautious of is when you square a positive number, right, it can turn into positive 2, but also when you square a negative number, it can turn into positive 2. So the answers are x minus 3 could be the positive square root of 2 or the negative square root of 2. So we get plus 3 plus 3. So getting x all by itself, we get 3 plus or minus the square root of 2 is equal to x. So what that means is that I have 3 plus root 2, 0, is one of my horizontal intercepts, and also 3 minus square root of 2, 0, is another. Now what we should do here is take those horizontal intercepts and give an approximation for what they are, right? Because the purpose is to really be able to graph these this function accurately. So 3 plus root 2 might not be the friendliest way of knowing where we cross the x-axis. So pull out our calculator, type in 3 plus root 2, and we get 4.41. And do the same thing with 3 minus root 2, and we should get 1.59. So that gives me an idea of where to place these. So I go to 4.41, puts me right about there. I go to 1.59, that puts me right about there. All right, so I've got a lot going on here. Now, one thing I want you to notice is if you look at 3, I've got an equal distance from the x value of my vertex to the left and to the right to get those x-intercepts. So we can also use that idea of symmetry. We know that we have symmetry with parabolas, right? If I go back a couple pages here, right, they look like they are perfectly symmetric about the line their vertex is on. And so we can use that property to get even more values. So for example, the fact that I'm going 3 to the left and up to a y value of 7 means that I could also go 3 to the right and up to that same y value of 7. So we can use that to kind of help us out here. All right, and then we also know from our work with just simply transformations of functions. This is just a regular y equals x squared graph that has been transformed by shifting it right 3 and down 2. All right, so we can also understand it from that perspective. So we're still going to go over 1, up 1. All right, and then then from here, we can graph our parabola. Okay. And a little bit of wobble here, I apologize. That looks a little better. And there we have it. In this example, we're going to basically do the same thing as in the last example. We're given this function here, and what we want to do is write it in vertex form and then be able to get a nice graph of it. Now, the difference between this one and the last one is that I have this -2 out here in front of my x squared. And if we backtrack here, the reason that we were able to figure out what to put in this slot to make our perfect square is because I broke it down as x plus or minus a number, x plus or minus a number, and I figured out, oh, it would have to be -3 to make this middle term. But the key was I broke this x squared into just x and x. So we want to be able to do the same thing here. But right now I've got a -2. So anytime there is a number here besides +1, we're going to start by factoring that number out. So I'm going to pull out a -2 first and see what I'm left with. So I would have a positive x squared minus 4x. And then just like in the last problem, we're going to add something and we're going to subtract something in order to create a perfect square. Now I leave the -7 out of it. I don't bother to factor a 2 out of there just because if you look back at the last example, that the number that was out here just kind of hung out. It wasn't playing a vital role in completing the square. And by the way, I don't think I used that term in the last example, but this process we're going through of creating a binomial, an x plus or x minus a number squared, is the process called completing the square. So we want this to turn into our perfect square. So in the last problem, the way that we went about it is we did say, let's kind of think ahead to the fact that we want something times itself to equal what's up here. And we said, let's look at the middle term and realize the middle term has to come from the outside plus the inside. And by doing that, we realize that putting a -2 in both of those slots is going to be the thing that does the trick. What I'd like to do in this example, though, is emphasize the fact that we can really kind of come up with a formulaic approach to this. So while it's nice to break it down this way, another way of approaching it is realizing that the answer for what to put in this place is always going to be half of the middle term squared. Okay, so I know this is going to be a 4, so I got to put a 4 in both of those spots, but this is always take the middle term, divide it in 2, and square it. And if I backtrack to that last example real quick, let's think about, okay, what is 9? Well, it's the middle term divided in half and then squared. And that, of course, gives me 9. So you can remember that. It's the middle term divided in half squared. That's the thing you add and subtract. Okay. All right, so with that, what we have is this x minus 2 times x minus 2. That turns into, comes from the x squared minus 4x plus 4. Okay, but I closed off my bracket a little too soon there, didn't I? So let me get rid of this bracket, right? Because we definitely need to remember the -4, right? That came from right there. All right, and then in the next step, I've got -2, and this is really x minus 2 squared minus 4, still in the bracket, minus 7. Okay, this doesn't look quite perfectly like vertex form yet, but that's because I need to distribute my -2 back through to everything. So this will be -2 times x minus 2 squared, and then -2 times -4 is positive 8, and then we have the minus 7 coming down from here. So in the end, we have -2 times x minus 2 squared plus 1. So we can see that our vertex is the point 2, 1. So we're right there. I can also see that because there's a negative here, I'm going to be opening downward. Okay. All right, now let's find our horizontal and vertical intercepts. Go ahead and switch colors here. All right, you have a little more room in your video notes to fill things in than I do. So let's start with the vertical intercept. Right? Pretty easy to see that g of 0 is just -7. So we've got 0, -7. All right. And as for horizontal intercepts, we're going to set our function equal to 0 and then figure out what x should be. So subtract 1 from both sides. -2 times x minus 2 squared. And then divide both sides by -2. Oops, sorry about that. So we get 1/2 is equal to x minus 2 squared. And of course we can take plus or minus the square root of 1/2 is x minus 2. So that means 2 plus or minus, and then the square root of 1 is 1, so I can really just have the square root in the denominator. So 2 plus or minus the square 1 over the square root of 2 is my x value. So that gives me a horizontal intercept of 2 plus 1 over root 2, 0, and 2 minus 1 over root 2, 0. But like we did in the last problem, what we should definitely do here is get an approximation. So my 2 plus 1 over root 2 is approximately 2.71, and my 2 minus 1 over root 2 is about 1.29. All right, so we can plot these values here. So 2.71 puts me right about there. 1.29 puts me right about there. My vertical intercept of 0, -7 puts me there. And then I can again say my vertex is at 2. So if I'm at y equals -7, 2 to the left of my vertex, I can also be at that same y value 2 to the right using symmetry. So here is our parabola. Now as I finish graphing this, a complaint you might have. The last two examples, we found our horizontal intercepts by setting the function equal to 0 and solving for x, and I've done it manually. And you might wonder, well, couldn't I have just used the quadratic formula? Sure, you could have just used the quadratic formula. So what you could have done for the horizontal asymptote portion is you could have just said 0 equals -2x squared. Sorry about that. Plus 8x minus 7, and done the quadratic formula and come up with those same two answers. I am completely fine with that. What I wanted to do is show you new techniques, particularly based off having your function in vertex form. But as far as the mechanics of how you choose to do this, you can make whatever choice makes the most sense for you. Okay, so what if I want to know the vertex of a function but I don't want to bother to actually do the completing the square and putting it in vertex form. So it turns out that there is a nice little formula that does this for us. So what we can do is say that the h value, or the x value of the vertex, is the formula negative b over 2a when you have it written out in standard form like this, ax squared plus bx plus c. And then, of course, the k value is just plugging that number, whatever it is, into the function. Okay. And the reason this works, by the way, actually has everything to do with the symmetry that we've just been talking about. So if I have a parabola, right, and that parabola has a vertex right here, well, of course, the parabola has a vertex. The idea is if I go a certain distance this way, and I go that same exact distance the other way, then the y value should be the same, right? And so if this is h, then I might consider, if this little distance here is x in both directions, then this x value would be h minus x, and this x value here would be h plus x. And so what you can say is that since their y values are the same, you can use this formula but plug in h minus x and h plus x in for it. So you can literally say a times h minus x squared plus b times h minus x plus c is equal to a times h plus x squared plus b times h plus x plus c. So you've got this set up, and I'm not going to go through all the details here because, number one, I think that it would be a good little exercise for you, and number two, it would take me a good 4 or 5 minutes to work through it. But this is a good little algebraic exercise for you. What I'd like you to do is expand all this out and solve for h. If you solve for h after a little bit of work, what you're going to find is that h is equal to negative b over 2a, right? The x's all kind of go away, and you're just left with this. H equals negative b over 2a. So that's why it all works, okay? So we keep that in our back pocket. If I have something in standard form, then I can find its vertex actually pretty easily using that formulaic approach. All right. The other little kind of proof that's nice to take a look at is why it is that the quadratic formula actually works. Okay. Now that we know how to complete the square, what we can do is realize that when you are solving this equation here, you can do it by completing the square. And so if you think about the process that we went through here with completing the square, we said first, any number that's here in front of the x squared, we factor out. And so I factor out my a, so that leaves me with x squared plus b divided by ax. And then I want to add something and subtract something. And then I'll just leave the c out here. Now it's b over a because, if I multiply a back through, I'll end up with bx in the middle term. And so the idea is, okay, well, what am I supposed to add and subtract? Okay, so what you end up doing is like we said before, you're going to add half of the middle term. So half of the middle term is b over 2a squared. And then, of course, you're going to subtract b over 2a squared. Now, just like on the last one, I'm not going to go through all of this with you. But what happens is if you continue this out, okay, and finish the process for completing the square, what you end up with is, after a lot of work, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you are working on this, I think it'd be great if you worked on this, and you kind of get stuck and have an algebraic question, please come see me about it. I'd love to work through it with you. But at least this kind of gives the rationale for why it is that the quadratic formula works. Okay, so now let's put all this into practice with a function. So here I want to graph the function, and a part of accurately sketching the function is to have the vertex. But this time I'm not going to put it in vertex form. Okay, so what I'm going to realize is that my a is -1, my b equals 1, and my c is equal to 2. So the x value of my vertex, the h, is -b over 2a. So that's -1 divided by 2 times -1, which would be 1/2. My k is equal to g of 1/2, right? So I'm just plugging in the x value into the function. So that's -1/2 squared plus 1/2 plus 2, which is -1/4 plus, might as well get common denominators here. So instead of 1/2, I'll put 2/4, and instead of 2, I'll put 8/4. So that's going to be 9/4. So my vertex is 1/2 9/4. All right. Now my vertical intercept is just g of 0, and I can see that that's equal to 2. So that's the point 0, 2. And then my horizontal intercepts, well, we just finished talking about the quadratic formula, and it's already in standard form, our function is, so hey, let's just use the quadratic formula. So this would give me x is equal to -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a, so 2 times -1. So that gives me x is equal to -1 plus or minus the square root 1, and this is going to be plus 8, so that would be 9 divided by -2, which is -1 plus or minus 3 divided by -2, which on the one hand, if I use the plus, is 2 over -2, which is -1. And on the other hand, if I use the minus, is -4 over -2, which is 2. So my horizontal intercepts are -1, 0, and 2, 0. So with all that, that should give us a pretty good idea of what this graph actually looks like. So we've got -1, 0, we've got 2, 0, we've got 0, 2, and then our vertex is at 1/2 9/4. So 9/4 is 2 1/4. So that puts me at x equals 1/2, y equals 2 1/4. So that puts me there. And then by symmetry, I could also know that I'm right here as well. All right, and so that gives me a good sense of what this function looks like. All right, so there's a graph of the function g of x equals -x squared plus x plus 2. This last example is meant just as a check of your understanding of what's going on here. And actually, I have a typo in your notes and in mine as well, I guess. I didn't want this to be a 13. I actually meant for this to be a 10. So if you could just, in your notes, change that 3 to a 0 so that you end up with 3x squared minus 12x plus 10. So in this one, I'm not going to go through all the steps. We just went through all those in the previous example. So what I would like you to do is pause the video and try this one all on your own. And then when you hit play again, I'll go ahead and write out the answers you should have arrived at. Okay, so let me go ahead and put those down. So you should have a vertical intercept of 0, 10. You should have horizontal intercepts written exactly as 2 plus the square root of 6 over 3, comma 0, and 2 minus the square root of 6 over 3, comma 0. But as we have in the past, we want to get approximations to those with our calculator. So this approximation here should give you about 2.82. And this one here should give you about 1.18. And then your vertex should be, I'm sorry, I'm having trouble grabbing the right color here. Your vertex should be 2, negative 2. All right, so putting that information together, you'll get a nice look at your graph here. So 2, negative 2. It's a positive 3 is the A, so it's going to open upward. And we can see that by the fact that we have 1.18 and 2.82 as the x-intercepts and 0, 10 as my y-intercept. And then I'll also go over here from the vertex x value of 2, go the same distance that way and also put that at 10. And then, so we should end up with this pretty skinny parabola here. All right, so hopefully you got something along those lines.